Okay, I think we're ready to do this. Let's see, I want to start by talking to you about the exponential function again, where how am I ever going to use this crap? Let's look at the graph so far for deaths in this country. This is what we've got so far from the other day. The last time I did this was a couple of days ago with you. We were here at, I believe we were at 425. Maybe I had to stick it to 550. Can't really remember, doesn't really matter. Then the next day, we shot up to 775. You see this exponential curve just growing, just straight up. I went, how many days is this? This was day 22 on one sheet. Then the 23rd and the 24th went on a second sheet. The 25th, yesterday's, because today is the 26th, where I am here, this would be about right here, and we hit 10, what do we hit, 1024, something like that, 1027, we'll be up here. I haven't drawn it and connected this yet, but you can see we're just skyrocketing. This is still in growth phase. We will, at some point, start leveling out, but I don't know when that's going to be. We will see. Got different opinions on that, depending on if you listen to scientists or politicians. Okay, logarithmic functions. We're playing the opposite game than we play with exponentials with logs. For instance, you know that addition and subtraction are opposite operations. 3 plus 5 equals 8. 8 minus 5 equals 3. One undoes the other. You know that multiplication and division are opposite operations. 3 times 5 is 15. 15 divided by 3 is 5, that sort of thing. You know that squaring, taking the square root of a function and squaring it are opposite operations. Those two will undo each other. Same way here, same thing going on here. What you've got in the top part of Thomas's explanation, top part of his first page, logarithmic function, y equals the log base b of x is called the logarithmic function with base b, little b down there, where y equals log base b of x is equivalent to b to the y equals x. That may not make a whole lot of sense to you. Let me see if I can make it make some sense with numbers. So if we've got 5 squared equals 25, you're okay with that? 5 times 5 equals 25. The opposite of that, turning that around into a log, would be the log, and then this base number, remember this is the base, this is the exponent, the base goes down here, then we're going to put the 2, the exponent will go over here. That's huge. I'll talk to you about that in a second. And then the other number, the only other number we have here is 25. Now that's a turned around way of saying, what do you have to raise 5 to? What exponent do you have to lay on to 5 to make it become 25? And of course, the exponent you have to lay on to 5 to make it become 25 is a 2. So log base 5 of 25 equals 2. When it's written in this form where the log is on the left, it's got a base and a number and that number, we can make ourselves a circle. So 5 squared equals 25. I'm going to do it both ways. I'll do a lot of circles and I'll do a lot of what do you have to lay on 5? What exponent do you have to raise 5 to make him become 25? Both of those. So this is what we're playing with. A lot fewer graphs in this section and the coming sections, and a lot more math. We'll be using our calculators for some of it. A lot of it will be logicking our way through. So let's look at the problems in Thomas's worksheet. Number 1, they're asking you on 1 through 4 to write each equation in exponential form. They're going to give you this form. They want you to rewrite it using an exponent like that. So the log of base 4 to base 4 of 16 equals 2. what you've got there is, what are you raising 4 to make it be 16? So what exponent do you have to put on 4 to make it be 16? When you've got it in the form log equals a number, you do a little circle there. So 4 squared equals 16. That's all they're asking you to do, is rearrange it. Put it in the exponential form instead of the logarithmic form. Number 2, we have the log of base 5, 0.2 equals -1. Again, they're asking you, what do you have to raise 5 to? What exponent do you have to put on 5 to make it become 2/10, to make it become 0.2? When it's in the form the log equals a number, we can do our little circle thing. 5 raised to the -1 power will give us 0.2. Remember that negative exponent says move me, move me, move me. So let's move him down. 1 over 5 to the first, which is just 1 over 5, equals 0.2. And sure enough, this is the fractional equivalent. This is the decimal equivalent. You can check that out in your calculator. If you're not sure, you can say 1 divided by 5 will give you that. Don't use the ABC key. Use the division key. 1 divided by 5. Or you can use a key that we haven't talked about a whole lot. I think I mentioned it once. It's a very cool key. This fraction to decimal above the PRB. So I'm going to put in there 0.2, and I'm going to hit the fraction to decimal key, second, and that one. And then we get 1/5. And you can go the other way. You can go second, fraction to decimal, and it'll give you back to the decimal. So that's back and forth. We're not going to use that a whole lot in this section. Just wanted to show you that. Number 3, we've got log base 8 of 1 equals a 0. This is a biggie. You're going to see this over and over and over again, not to 8, but to other numbers. We can put any base there. Let me show you what we're doing. What do you have to raise 8 to make them become a 1? Let's do the circle. So 8 raised to the 0 power is a 1. You know anything raised to the 0 power is a 1. So that any log of any number of 1 equals 0 is going to give us, is going to give a 0. Raising any number to the 0 power will give you a 1. We'll see that over and over. And see, over and over, we see it again right here. Log base 23 of 1 equals 0. Again, what do you have to raise 23 to make it become a 1? Let's see, I want to be sure we're on the screen still. There's the 0, good deal. Okay, so let me look at the circle. So we've got 23 raised to the 0 power will give us a 1, and yeah, that works. All right, on 5 through 7, they want you to take the exponential and write it into logarithmic form. Okay, this is also just a very set way. These are circles here. You can take them around in a circular fashion. This is similar to that. You just need to know the pattern. So when you're asked to write it in logarithmic form and you're given an exponential, put the word log there. It just means we're going to do the opposite of raising it to an exponent. Then the base, that big number, becomes the little number here. It's a base. Then the exponent always will be over here. Always the answer to a logarithmic problem is going to be an exponent. We're always going to be saying, what do we have to raise 2 to become whatever this number is? So the base will be the little number here, big number becomes a little number. The exponent will always be the answer, and the third number there will just sit there. So what do you have to raise 2 to make them become 16? You can do a circle to make sure it works. 2 to the 4th equals 16, and that's where we started, so you're in a good place. Number 6, 27 raised to the 1/3 equals 3. We're trying to, just to remind you, this 1/3, let me scribble it right in here. Remember, that means the cube root of 27. So when we've got a fractional exponent, that's the same thing as building a radical and putting the denominator right up here. And sure enough, the cube root of 27 is 3, just so you understand it. We're not going to convert it to that. I want to make sure you understand it as that. So we're converting this into a logarithmic equation. log, we want the base down here, the base is 27. Set it equal to something, always back here, the exponent is the answer. To a logarithmic, the exponent is the answer. So we'll always set it equal to the exponent. And then we'll put the other number right there. That says, what do we have to raise 27 to make it become a 3? If we're taking a big number and making it into a smaller number, we need a fraction. Over here, we took a little number and made him bigger, so we need a big number. A whole number, bigger than bigger than 1. Here we're taking a big number and squishing them down, so that's going to be a fractional number always. Not a big deal. You're not going to have to, I'm not sure that's too useful. Okay, now let's take a fraction. 1/4 raised to the negative 2 power will give you 16. Remember, a negative says move me, move me, move me, so that 4 jumps on top, and 4 squared is 16. So this is true. We just need to rearrange it into a logarithmic equation. So log, remember the base will become the base down here. Always the answer to a logarithmic is that exponent, and then the spare number right there. What do you have to raise 1/4 to become 16? You have to raise it to a negative 2. The negative flips us around, puts him on top, and then the squared, of course, makes him become 16. All right, 8 through 10, we are evaluating. We're coming up with an answer for these guys. Let's see how I'm doing on the screen. Oh, just about. Let me scoot this guy down. Is that gonna? Yeah, it's perfect. Okay. Okay. Number 8, we're evaluating these guys, coming up with an answer. So log base 12 of 144. Okay, when you're looking for an answer, I think the easiest thing to do is to say equals x, because we're looking for an answer. What we're asked to do is find what do you have to raise 12 to make him become 144. So you may know what that is. If you don't know what it is, or you just know what it is, but you want to develop a pattern, develop a habit of how to do these for all times, for when you don't know what they are, set yourself up a little circle. So 12 to the x power equals 144, and then you're looking at it. If you don't know it, what you're going to need to be doing is to practice this with your calculator. You're going to try it. Let's see, 12 humpy 2. Sure enough, that's 144. That worked. So x here equals 2. 12 squared will give you 144. So you're going to be playing a little bit of guessing around with your calculator occasionally on these. Number 9, we're evaluating log base 4 of 64. Again, we're looking for what that is, so let's say equals x. Make ourselves a circle. So 4 to the x equals 64. Again, if you don't know what you have to raise 4 to make him be 64, grab your calculator and play a little bit. 4 to the second power doesn't equal 64, it equals 16. 4 to the third power equals 64, so x is a 3. So log base 4 of 64 is 3. What do you have to raise 4 to make him be 64? Right there. Number 10, log base 5 of 1 over 125. Again, if you're looking for an answer, let's set it up. Do a circle-y thing. 5 raised to the x power will give us 125. Okay, first thing I see is that the action over here is happening in the denominator. So I know this is going to be a negative number. So let's see, x is going to be a negative number. That will send it down to the bottom. So I've still got the x hanging out there. So the ones match. I'm looking at 5 to the x equals 125. Again, grab your calculator if you don't know, but 5 to the third power will give you 125. So here it'll be a 3. But when we go back up to the original problem, it's going to have a negative on it to send that 5 to the denominator. So x is going to have to be a negative 3. Play with that if you're not sure. 5 to the negative 3 equals 1 over 125. Yeah, the negative will drop it down here, and the cubed will make it match. So now we match. So -3 is the answer. 5 is a big number. It's going to become a very small number. This is going to have to lower it a lot. So -3 is a good number. Okay, then Thomas reminds you of two things that I've already talked about a little bit before. The square root of x is x to the, equals x. Let me start over there. The square root of x, that radical, you know, has an index of 2. That's the same thing as x to the 1/2. So those are going to be the same things, and we'll play with that just like we played with it somewhere up here. Oh, where I was just reminding you that 27 to the 1/3 up above. 27 to the 1/3 equals the cube root of 27. Same thing. That's what we're doing in this next little guy. So the cube root of x is the same thing as x to the 1/3, where the denominator is the index. All right, let's look at number 11. 11 is the log of 64, log base 64 of 8. Again, we're looking for an answer just like we were looking for in 8, 9, 10, and 11. They're asking you to evaluate it. So set it equal to x. We're asking ourselves, what do you have to raise 64 to make him become an 8? We're going to have to make that number smaller, 64 down to 8. So this is going to have to be at least a fraction. Let's set it up. 64 raised to the x power equals 8. Couple of ways of thinking of this. You know that this has to do with square root, and you know you need to lower this number. So you know that the square root of 64 equals 8. You can handle that. And now they want you to turn this radical into an exponent. So just like up here, a square root is equal to x to the 1/2. This will be 64 to the 1/2 will give you an 8. You can test that. Turn your calculator on. 64 humpy raised to the, and then you can put in 1/2. 1 ABC2 and hit the enter sign, and you will get an 8. Another way of doing that, 64 raised to the 0.5, because that's the equivalent of 1/2, and you'll get an 8. So if you want to use fraction or decimal, it doesn't really matter. Okay, let's go to the next page. Okay, up at the top with common logarithmic function and natural logarithmic function, he's telling you two things that really, really matter to us. So let's look at common log first. We're going to have log with no base written there. For instance, the example, the number 12. Number 12 is log of 100. This is number 12. Log with no base of 100. This is called a common log, where there is no base written there. It's understood, if you don't show one there, to be a 10. So when it says, when you're missing the base, it's understood to be a 10. And we'll do the problem the same way. This one asks us to evaluate each expression just like we were doing in 8 through 11. So we're going to set it up like this. 10 to what power will give you 100? Well, you know that 10 squared will give you 100. You can play around with your calculator if that's not super comfortable to you. So this is called common log, where the base is missing. Let's look at number 13. It's similar before we move on to natural log. We've got log no base of decimal point and then 3 zeros. It's asking you, what do you have to raise a 10 to become 1/10, hundredths, thousandths, 10,000ths? What do you have to raise 10 to, this understood 10, to become 1/10,000th? Again, set it up like this. We know there's a 10 there. So 10 to the x equals 1, 2, 3, and a 1. What we do know there, or what you may not know, but you're about to learn, is that when you're taking this 10, if you raise it to the first power, you'll get 10. If you raise it to the negative 1, 10 to the negative 1 equals 1/10. Move it down, and that's 0.1. 10 to the negative 2 is 1 over 100, and that's 0.01. Can you see how the number there indicates the number of numbers here? So we have two numbers here, that's 10 to the negative 2. We have one number, that's 10 to the negative 1. We have four numbers, so that'll be 10 to the negative 4 will give us 1/10,000th. Let's check that in your calculator. Let me show you how to do that. You have even a special key for that. You have a power of 10 right up here above the log button. So let's get to that button, hit second and then log, and it says 10 to some power. So then put in -4, use the negative button down here, not the subtract button, hit equals, and there you go, 1/10,000th. So you can play around with the 10. You don't have to do that. You can just absolutely go straight forward. 10 humpy -4 will give you the same thing. So either one, you can use this 10 key here in the gutter, second log, or you can go 10 raised to the. Okay, so that's the two introducing you to logs, common logs. Let's look at natural logs now. Number 14 and 15. 14 and 15 have to do with E, the key of E. So we've got the natural log, ln. It's the same thing as a log, except it's using as its base an E. So it's an E right there. Let me rewrite that. It looks too LE. There we go. So the natural log of e to the -3. What you understand here, this has no base. The base for this one is an E. So let's do that kind of thing. The base for the natural log means you're dealing with E. So that's natural growth and decay. That is, how many leaves will be in the forest, how many leaves will be on a tree, the half-life of minerals, or of the half-life of carbon, the half-life of anything that decays, how tall people will be at certain times, predictive of their age, that kind of mess. So this is naturally what's happening in our world. It's understood to have an E there. Now, number 14 wants us to evaluate it, so let's do the e to the x equals e to the -3. When the bases match, the exponents match. So x is a -3. So in this particular problem, we've got natural log of e to the -3 is -3. We found -3 as our answer. Let me get this set up for the rest of the page. So the natural log of e to the -3 is a -3. What do you have to raise that understood e to get it to be e to the -3? Well, that seems pretty obvious, because once you set it up, what do you raise an e to make him be e to the -3? Bases match, exponents match. Number 15 is similar. We've got the natural log of e to the 10th. You don't have a base written in here. You understand it to be an E. So let's set this up, do the circle. E to the x equals e to the 10th. When the bases match, the exponents match. So the answer there to that problem is 10. Okay, number 16 through 19 ask you to use your calculator. So we're just getting used to what's going on with logs and the buttons in your calculator. You should have seen how you had to do it when you didn't have a calculator. It was fun. It was tables in the back of the book. But that's different now, of course. Check your answer by using the exponential form. Okay, so let's look at the first one. Number 16 says log of 200. We'll call that common log of 200 because there is no base. It's understood to be a 10. So they're asking us, what do we have to raise 10 to become 200? Okay, let's look at that. If we raise 10 to the first power, that's only 10. We want it to be 200. If we raise 10 to the second power, that becomes 100. Getting there. If we raise 10 to the third power, that's a 1 with 3 zeros. That's 1,000, that's way too much. So we're trying to find an exponent that we can raise 10 to that will get us to 200. So we can see it needs to be more than 2, but not quite 3. That's way too big. So this is saying 10 to the x equals 200. That's the idea that we're asked to find here. You don't need to do all that in your calculator. You don't need to understand all that, but boy, I wish you would. I need for you to, because of where we're going, what we're doing even in this section. So continue to understand what it's saying. Remember, the problem originally didn't have this 10 here. It's a common log. It just said log of 200, common log of 200, because it didn't indicate a base. So that's this first key underneath the second shift key. That's the log key. So log of 200 equals, and there we go, that's our answer. So the log of 200, the common log of common indicating there's a 10 for a base, the common log of 200 equals 2.3010. They're they're asking to round to 4 places, so we need a 5th number. There's the 4th number. The 5th number tells you just drop it off. So the common log is approximately 2.3010. It's really simple to do in your calculator. Just hit log of 200. Okay, the next one, number 17. We're looking at the log, common log of 0.074. Again, that's asking us, what do you have to raise 10 to become 0.074? So 10 to the 0 power, you know, is a 1. 10 to the negative 1 is 0.1. 10 to the negative 2 is 0.01. 10 to the negative 3 is 0.001. 3 numbers here, 3 there, like we talked about earlier. So we want our number is 0.74. So our number needs to be somewhere in here between -2 and -3. Again, you don't need to go through all that. I just want to be sure you're thinking about it. So we're going to do log of, you can put a 0 in there if you want to, 0.074 equals, and we get, ooh, what did I do wrong? I did something wrong there because I've got mine between 2.074. Oh yeah, geez, sorry. Okay, so 0.74 is on its way between these two. 0.1 to 1. This is like 10, this is like 1, and I'm at 7, so it'll be in this area. Big boo-boo. So the log of the common log of 0.074 is -1.13076. There's our 4th number past the decimal. 6 says go up, so this becomes an 8, and that goes away. So -1.1308 approximately. We've rounded it, so all that indicates. Okay, let's look at number 18. Natural log of 200, ln of 200. What do you have to raise e to make him be 200? E is about 2.7. So we're going to have, it's like 2 or 3, rounds to 3. So 3 to the 4th is 81. 3 to the 5th is 243. So we're going to be between 4 and 5 in there. Let's see. Grab your calculator. Let me just make sure you know what we're doing here. Got an E there. E to the x equals 200 is our idea. You don't need to go through that though. Grab natural log. That's that button right there. Natural log is the second one down. Natural log of 200. So we're just reading it straight off of here. Natural log of 200 equals 5.29831. 4th digit, 5th digit dies out. So 5.2983 approximate. Check something here. Let's see. Moving to the next page. My notes. Let's see, I had told you that, just off the cuff, 3 to the 4th power is 81, 3 to the 5th power is 243. Oh, okay, so 3 raised to the 5th power is 243. E is not 3. E is 2.71-ish. So that's why we ended up with more than 5, because this is not a 3. It's smaller than 3. Which reminds me, we're supposed to be checking these. So let's go back to number 16. So you can see that 10 raised to the, let's back up. Common log of 200 equals 2.3010. That's telling us that 10 to the 2.3010 will give us a 200. So 10, I'll have to get to it by the second key. 10 raised to the 2.3010 equals, and there's 199.986, so 99, that rounds up to 200. So that one works. Let's look at number 17. Again, 10 to what will give us 0.074, and we found out it was negative 1.1308. So let's raise 10. You can do it this way too. 10 Humpy negative 1.1308, and sure enough, that'll give you 0.07399, which is 0.074, rounded up a little bit. Remember, we rounded this, so our answer will not be exact. And then in this one, we've got we need natural log of 200. We found out that that number is about 5.2983. So we're going to raise E to the 5.2983 to get 200. So find E, it's in the second ln. So second ln will give us E raised to the 5.2983, and that gives us 199.996, so that's 200. Okay, let's look at number 19. We're looking for the natural log of 1.005. So just going straight forward, natural log of 1.005 equals 2.7319. So we can just drop that off. Fourth digit, look to the fifth digit. So this is saying E raised to the 2.7319 ought to give us this. Let's see if that works. E raised to the 2.7319 gives us, okay, well I mucked that one up. E to the 2.7319 equals 15. Doing something wrong there. Let me see, maybe I pushed something wrong here. Let's see. Natural log of 1.005 equals, oh, there's a problem. This answer is wrong. Let's see, I don't know what I pushed. I pushed something wrong. I guess I could go back and look, but I'm not going to have to start all over. No way to pause this and back it up. Not that sophisticated. So I just pushed the wrong button. Maybe I did log. Let's see, log of 1.005. Nope, I don't know. Doesn't matter. Okay, so let's start number 19 all over again. Number 19 is natural log of 1.005. So I've got the natural log of 1.005 equals, there we go, decimal point 00498. Fourth number, fifth number tells you to round up. So if you're rounding up 49, you've got to round that up. That's going to round to 50. So there's our answer, and that's an approximate answer, 0050. And as a check, E raised to the decimal point 0050 sure as hell better give us 1.005. Let's look at that. Let's look at E raised to the point 0050, and we get 1.005. Wonderful. Okay, so don't know, hit something wrong. Okay, then in that double-lined area, apply basic properties of logarithms. There's some those truths that they talk about with different, identity elements, that kind of thing, like 5 times 1 is 5 with multiplication. Anything divided by 1 will give you the number itself, like 5 divided by 1. So we're looking at those kind of truths in 20 through 28. Let me get us a new piece of paper. Start that fresh. You'll not have to memorize these truths. The better you get at them, the quicker your work will go, but it's just not that big a deal to memorize them. So no worries if you have to work every one of them out one at a time as we go. Some of you will memorize them, some of you won't. See, what do we have left in this class? Whew. This is 4.2. We've got 4.3 and 4.4 that deal more with logarithms and exponentials. And then we've got a really super easy 8.1 section that deals with series and patterns. That's kind of cool and fun and easy. And then we've got 1.6, which is other kinds of equations. We're working on factoring in a little bit different ways. So we're wrapping this up, folks. Let's see. Let me go a little bit further. There we go. Okay, so this is still 4.2 Thomas's, and we are finishing it up a little bit. Okay, instead of concentrating on the B's and the X's and all that, let's just jump into it and we'll look at them one at a time. Number 20, log base 19 of 19. We're trying to simplify the expression. We're asked to evaluate this, so let's put an X. They're asking us, what do you have to raise 19 to become 19? What exponent do you have to lay on 19 to make him be 19? If you're doing the circle thing, you're looking at 19 to the x power equals 19. So you can see that's a 1. 19 to the first power will give you 19. So a log of base of any number to its number will give you a 1. What do you raise 19? What do you raise 25 to become 25? A 1, that kind of thing. That's one of the principles. You don't have to memorize 19, 19 equals 1. You can just make the circle, put an equals x, make a circle, and then it makes sense to you. So you don't need to worry about shortcuts. Okay, number 21, log of 10. There is no base written here, so this is a common log. We understand that to be a 10. So what do you have to raise 10 to become 10? I'm going to put an x there. This is very similar to number 20, where the base and the number match. So put a little 10 there. 10 raised to what power will give you 10? Obviously, it's a 1. So when the base and the number match, the answer is a 1. No need to memorize that. It takes 2 seconds to write it out and look at it and know it. Number 22, the natural log of e. Same problem as number 21, same problem as number 20. We're asked, or understand there's an e as a base there. What do you have to raise e to make him be an e? So put in your little understood e there, set it equal to x, make yourself a little circle. What do you have to raise e to make him be e? Well, that'd just be a 1. All of these, same principle. When the base matches the number, when the base matches the number, when the base matches the number, the answer is a 1. Number 23. Another principle here that we're going to look at in number 23 and number 24. Log base 273 of 1. What is that equal to? What do you have to raise 273 to make it become a 1? Okay, let's set it up with an equals x. Do a circle. 273 raised to what power will give you a 1? I'll remind you that any number raised to the 0 power gives you a 1. So this x here, the exponent, is a 0. Remember, the answer to a log is always an exponent. So that exponent, 0, will take any number raised to the 0 power will give you a 1. So 0 is the answer there. Number 24, log of base 1/8 of 1. Again, what do you have to raise 1/8 to have it become a 1? If you know it's just like this problem, you're done. If you don't, you set it up. You say, make a circle. 1/8 raised to the x power will give you a 1. Every number raised to the 0 power will give you a 1. So 0 power is the x answer. Number 25. This is a funky little one. Let's dissect this. Okay. So, log base 30. What do you have to do to 30 to raise it to 30 to the 10th? To make it become 30 to the 10th? What do you have to raise this guy to? What exponent do you have to lay on him to make him become 30 to the 10th? Let's put an equals x here. Let's do our little circle. 30 to the x power equals 30 to the 10th power. When the bases match, the exponents match. So x equals 10. So what that says, let's put it back in here. Log base 30 of 30 to the 10th power is 10. 30 to the 10th power will give you 30 to the 10th power. Seems pretty obvious, doesn't it? I mean, when you look at it like that, it's a gimme. So 30, what do you have to raise them to become 30 to the 10th? You have to raise them to the 10th power. Okay, let me test and see how low I can go on this paper. Okay, so we're ready to move down. Yourself some perspective there. All right, let's look at number 26. Natural log, we want to get e to the negative 12. So natural log is taking e, an understood e, and we're asking ourselves, what do we have to raise it to make it be e to the negative 12? Same problem as number 25 there. Put an x there. You know this understood e there. Let's make our circle. E to what power will give us e to the negative 12? The bases match, the exponents match. So the answer is negative 12. Let's rewrite that. Natural log of e to the negative 12 equals negative 12. E raised to the negative 12 will give you e to the negative 12. Seems kind of basic sometimes if you can stand back and look at that. Number 27 and 28, we're doing something a little bit different. This is just weird. 10 raised to the log of 14. So this is not a log problem. Log is not sitting, or natural log is not sitting on the ground. This is an exponent. So this is just saying take 10 and raise it to the log, the common log of 14. It's calculator time. So you've got a 10, put a 10 in. You can put it in either by using 10 to the x up here, or you can just put it in, manually put it in. I'm going to do it both ways just so we can go over it a couple times. So the first way I'm going to use is this 10 to the x key. Second log will give us 10 raised to the, and then I want to put in common log of 14. So I'm going to hit the log button and hit 14, and you can close out the parenthesis if you want, but you don't need to. And there we go. We get 14. So what we know is that 10 raised to the 10 to the 14, what do you have to do, raise 10 to the 14th? You get 14. We will deal with this a little bit more in another way after we get a little more used to logs. So I think we're just going to let that one sit. Not going to go over it a whole bunch of times or explain why that works. Let's look at number 28. We've got, again, similar, oh, I want to go over this one again. I want to use the other key. So if we use 10 humpy, then you're still just going to put in log of 14 there, and that's still 10 raised to the log of 14. Hit the equal sign, and you'll get a 14. Okay, number 28. The problem, again, is different from these others. These are log problems. These are exponent problems, these last two. Raised to the log base 8 of 5. Okay. Let's make that a logarithmic problem, because I think that's probably the easiest way to explain it to you. So let's set it up like that. The way to rearrange this is, what do we have to, 8 is our base, put log, 8 is our base, x is going to be what we're going to get, and log base 8 of 5 is the exponent. Remember, in a logarithmic equation, this is a logarithmic equation, the answer will be the exponent. So now we've got log base 8. When those match, these match. So x equals 5. So taking us back to this problem, 8 raised to the log base 8 of 5 is going to give you a 5. You know, you can memorize this idea, so that's the answer. These are not huge. I mean, this is easy. This is an exponent. 10, put that in there because it's a common log. This, we can't change the log in our calculator. We can't put in log base 8. We can put in, you know, this log key is common log. This is natural log. But we're not able to manipulate this and get a little 8 out of that, a base 8 out of that. We're going to find out how to deal with that in 4.3 or 4.4. But for right now, not a big deal. Just so you know it is good enough. If there's some funky things going on there. Okay, let's move forward. Let's look at 29 and 30. 29 and 30 are graphs. We're looking at what does this look like? What does a log function look like? So we've got just these two that we're doing, 29 and 30, light on graphs for a while. Let's see, it asks you to graph y equals the log base 3 of x. And notice the parenthesis out there. He says rewrite into an exponential form and select values for y first. You know, what the hell does that mean? Let me show you what that means. The problem on 29 is y equals the log base 3 of x. Let's change that into an exponential form. We're used to having this y over here, so I'm going to get rid of that and put it over there. So log base 3 of x equals y. Changing this into an exponential, that's the base. You know that always a log equals an exponent, so the answer is always an exponent, and then x goes by himself. So this is what we're going to graph. We were graphing them last section. Let's graph it again. However, this time, whenever the exponent, whatever variable the exponent is, that's where you want to put -2, -1, 0, 1, 2. We were putting it for the x column because back when we were doing 4.1, we had x's right there. This time we got y's. So when you have whatever your exponent is, that's where you're going to put your little series of 5 numbers. So we've got 3 to the -2. You know that says move me, move me, move me. So we get 1 over 9 out of that. So this becomes 1 out of 9. 3 to the -1, move me, move me, move me. We get 1/3. 3 to the 0 power, that's a 1. 3 to the first power, and 3 to the second power. Okay, let's graph that. So we've got 1/9, -2. 1/9 on the x-axis comes to the right, but just barely, and then -2, so just really hugging the x-axis. 1/3 is barely more out at -1. 1, 0. 3, 1. And 9, 6, 7, 8, 9. Okay, we go out to 9, 2. So there's our logarithmic function graph. So it does something like this, and then on out. So that's all they want us to do there. I want to point out a couple of things to you that'll be useful to you in the future. This has got a vertical asymptote of x equals 0. Vertical asymptotes are always x equals lines, and we're going through 0 on the x-axis. So that's a vertical asymptote of x equals 0. Just for giggles, let's look at the domain and range. Let me get a black marker for that. It's easier for you to see, I would imagine. Let me just put it here. The domain here, what are we using up of the x-axis? Well, we're not using any of the negative side. None of that is being used. We get really, really close to 0, but not quite on this x-axis. So parenthesis, it won't hit 0, and this will take us on the x-axis all the way out to infinity. On the range, that's what are we using up of the thermometer? We're going to go all the way down here, getting closer and closer and closer to the x-axis, but never quite reaching it. So we do go down to negative infinity on the thermometer. And how high up are we going to go? Well, this will carry us up, so to positive infinity. We'll be using those later. Thomas's exercise didn't ask you to find that. I just thought it'd be helpful for you to look at that, be thinking about that. Okay, let's look at number 30. Number 30, graph y equals log base 2 of x plus 1 plus 2. He says, hint, start by graphing y equals log base 2 of x. So y equals log base 2 of x. When I have a log problem, I want the equals on this side, so I'm going to get rid of it there, move it over to there. And I want to, just like we did on number 29, I want to rearrange into an exponential equation. So you know that what we've got here is the base, The answer to a log problem is always the exponent, and then the x goes over there. So this is the exponential right here. A log problem always has as its answer the exponent. That's why that's there. So we've got the same situation as before. What we want to do is we always want to make sure our -2 to +2 fall under that, whatever variable you see there in the exponent. So 2 to the -2 says move me, move me, move me. So we get 1/4 for that. 2 to the -1, it's just going to be 1/2. 2 to the 0, anybody raised to the 0. 2 to the first, 2 to the second. And now let's graph that. I'm going to start by graphing that. So 1/4, -2. 1/2, -1. 1 0, everybody's going to go through 1 0. Remember on the exponentials, everybody's going through 0 1. Now it's the flip there. We'll explore that a little bit later. 2 1, and then 4 2. So that's f of x, or the main one, the parent function. That's the log base 2 of x. We were asked to shift it, x plus 1 plus 2. So let's talk about what that does. You know what that does. This piece is a liar, and this piece stays the same. So an x plus 1 tells you're going to go -1 to the left, or 1 to the left, I suppose. -1 to the left for each of these points, and then 2 up. This will be the opposite because it's attached to an x. So let's see what we're going to do. I'm going to start with this belly button. That's the easiest, 0 1. I'm going to go -1 to the left and then up 2. So this is where the turning point will be for the actual number 30. I can do the same thing with any of these. I know this point is going to be 1 to the left and up 2. This point's going to be 1 to the left and up 2. This point's going to be 1 to the left and up 2. This point's going to be 1 to the left and up 2. So we end up with that sort of thing. That's what our new graph will look like. And then let's look at that asymptote. The vertical asymptote for the original is x equals 0, but we've scooted our graph over. So our vertical asymptote, which they're not asking you for, Thomas didn't ask you for this, but our vertical asymptote is x equals -1. Right there, you can see it, x equals -1, what that number is. It just shifts our guy over. Domain and range, let's look at that a little bit. The domain of the red line we're talking about. The domain is going to be, what do we use up of the x-axis? We start using it up at -1, but we don't ever touch -1 because it's an asymptote all the way out to infinity. The range will be -infinity to +infinity. Again, we'll explore that a little bit more later, but I want you to have the feel of that now. Okay, so that's number 30. Go to the next page and bam, we've gone to number 33. We skipped 31, skipped 32. My guess is, oh, phooey, I did that again. Let's see, so let me show off to you again. Doesn't matter what color I use. Let me mark all of this with a marker that is an Expo marker, that is a whiteboard marker. And then while it's still wet, no, that didn't do so much good. I'll play with that when I'm done here. Okay, let's look at number 33. 33 is talking about stars. I had to learn a little bit about astronomy, not astrology, astronomy, to help you with this problem. What we're talking about here is big M stands for absolute magnitude. Absolute magnitude means the real brightness of stars. The real brightness of stars. Little m means the apparent brightness of stars. How bright it appears to us. So we've got the sun, that's a star in our solar system. Sirius is a star in our solar system. One is a lot further away. We're not sure how actual, if we could walk up to them, how bright would they be? This is a little like saying, if I had a flashlight in my hand and my neighbor across the street had her porch light on, well, you know that the porch light is brighter than the flashlight in my hand. Let me go close my window because I'm not sure if you can hear that. Okay, so this flashlight in my hand isn't going to be as bright as the porch light across the street. But to me, it seems like it. So the apparent brightness of my flashlight in my hand as I stare at it is much brighter than the porch light. But the real brightness, the porch light is a lot brighter than the little flashlight in my hand. So that's what we're trying to do with this formula, is figure out which ones are brighter. How can we tell what's brighter? The scientists a lot smarter than me came up with this idea. Let me read through this so we can talk about it. The absolute magnitude, what's real, of a star is the apparent magnitude, the amount that it seems like it is, that a star would have if it were placed 10 parsecs from Earth. So if we put it 10 parsecs from Earth, and just so you know, a parsec is about 3.26 light years away. So this would be like 32.6, 33 light years away from the Earth. And we're trying to, if we placed everything 33 light years away from Earth, we placed everything 33 parsec light years away from Earth, how would they then compare? If I put my flashlight and my neighbor's porch light the same distance from me, then it'd be easy to tell. So that's what we're doing here, is trying to place these two stars, Sirius and the sun, a certain distance away from us, the same distance away from us, and then decide who's brighter. The lower the value of the magnitude, the brighter the star. Our sun has an apparent magnitude of negative 26.74, so we're just giving the information now. The brightest star in our night sky is Sirius, the dog star, with an apparent magnitude of negative 1.44. The sun appears so bright because it's very close, astronomically speaking. Here's our formula. That's important. Big M, the real brightness of it, is equal to the apparent brightness minus 5 times the log of the distance divided by 10, its actual distance divided by 10. It relates a star's absolute magnitude, big M, little m, apparent magnitude, and its distance d from Earth in parsecs, the real distance that it is. So we've got, if Sirius is 2.637 parsecs from Earth and the sun is 4.887 times 10 to the negative 6 parsecs from Earth, what's the absolute magnitude of each star? So they're asking us for the absolute, the real brightness of each star, giving us everything else we need to know. They've told us the apparent brightness, the apparent magnitude, that's up in the paragraph, negative 26 and negative 1. And we know where 5 is, we know how to find a log, and their distances is in the last paragraph, how far away they really are from Earth. So let's do this. Let's look first at Sirius. Its absolute brightness is equal to its apparent brightness. Well, let me write the formula as we have it. Minus 5 times the log of the distance divided by 10. So its absolute brightness is equal to its apparent brightness, negative 1.44. You find that in the paragraph above, minus 5 times the log of the distance that Sirius is from Earth, and you can find that in the bottom paragraph. If Sirius is 2.637 parsecs from Earth, so we've got that. That's what we need to compute with our calculators. I'm going to do it a little bit at a time. Let's see, so m equals negative 1.44 minus 5 times the log 2.637 divided by 10. Let me turn it on. 2.637 divided by 10 moves the decimal place over, and you get 0.2637. Now we need to take the log of that. So the absolute brightness of this is negative 1.44 minus 5 times, and then I'm going to take the log of 0.2637, and that gives me a negative 0.578 dot dot dot. I'm immediately going to turn around and multiply it times negative 5, and I get a positive 2.8944. And then I'm going to subtract negative 1.44 from it. So minus 1.44, and I'm getting 1.45445. Let's say, let's round that place up. It doesn't really matter to me where you round it up. So this is our number. It's got a positive on it just to indicate very clearly that it's a positive 1.45. Just in case you care, I looked it up, and that is very, very close to the number that is the actual number for Sirius for its real brightness. If we put the flashlight and the porch light together, we know that this would have that level of brightness. It really isn't a value until we compare it to something else. So let's compare it to the sun. Let's see, same formula. We need the apparent brightness of the sun. The apparent brightness of the sun is in that top paragraph, negative 26.74 minus 5 times the log of the distance that it is from Earth. That's 4.887 times 10 to the negative 6 over 10. Okay, let's go figure that. Big M equals negative 26.74 minus 5 times the log. Let's do this division. This is written in scientific notation rather than give us decimal point 0.00000045, that kind of thing, 5 zeros, and then 458 or 4887. What they've done is do it in scientific notation. You don't have to become a scientist for this. You're good. Can you see that out there? Yeah, okay, there. So, 4.887 times, and you can use 10 to the, oops, I used log instead. I forgot I had to do second. So 4.887 times 10 raised to the negative 6 equals and see we've got 1, 2, 3, 4, 5, 6 places between the 4 and the 8. They moved it over -6 times, carrying it to the negative direction. So that's the equivalent, not in scientific notation. We want to divide that by 10. We get that number. I want to find the log of that, so I'm going to need to write that down. So I've got a decimal point, and then we should have 6 zeros. 7 zeros, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. And then 4, 8, 9. Okay. They've rounded. 4, 8, 8, 7, they rounded for us. So I think it doesn't matter. It's such a tiny difference down there, that many decimal points over. So I want to take the log of that. So log of decimal point 1, 2, 3, 4, 5, 6, 4, 8, 8, 7 if you want to be correct. 4, 8, 9 is fine too. Take the log of that, and I'm getting -6.3 and some change. I'm just going to leave it like that. And then I've got to multiply now times -5 times -5. That gives me a plus 31.55 blah blah blah. Then I'm going to subtract 26.74 from that, and I'm getting 4.815. I'm not too concerned about how you round, with a plus sign there. So the sun has a 4.815, Sirius has a 0.145. I did not investigate enough, but what I'm looking at from what Thomas wrote, he says the lower the value of the magnitude, the brighter the star. So this one has a lower magnitude. That says to me Sirius is brighter than the sun. I'll check on that and let you know in the next video. First off, in the next video on my 4.2, just because that's interesting to know which one's brighter. I guess it's interesting, but it's valuable here in this problem. I don't know what that means, or I don't know how that indicates. I mean, come on, 4 is bigger than 1, so it ought to be brighter. But Thomas has got that line in there, so I'm going to check on that, and I will let you know. I'll see you next time.